39. The x exponential random variable with parameter lambda equals 1. Compute the probability density function with the random variable y defined by log x. So in 39, we're going to do the same thing essentially as this. You're starting with x has exponential variable with right. This. Are there any questions on this? This is okay. So actually, we are going to check that this is greater than 5. That's not be good enough. Because if there was another approximation we wanted to use, which would have been the Poisson approximation, we would need this to be less than or equal to 5, and that is certainly not satisfied. So if we have to do an approximation, it'll have to be the normal approximation. So on the review sheet, I said check that it's greater than 10. It's a better approximation, it's greater than 10. But if it's greater than 5, it's still a good enough approximation, normal approximation. Less than or equal to 5, use Poisson. All right. So what we raise this. Let's do problem 39.
I dreamed I think I dreamt you say that we can come in with a formula sheet. Did I dream that, or was that?
Did I just say that? No, that was just when you were dreaming.
Oh, I might remember.
No, you're allowed a formula sheet.
Okay.
Yeah. 8.5 by 11, normal size front and back.
Exactly, yeah.
Sweet. You can
8.5 by
write
11.
as small as you want.
Right, yeah, that size sheet, right.
Actually, you
No
said on the
poster
review
board?
sheet, you said that
No
it was.
poster boards, we're not allowed to bring in like a giant poster.
If we all combine and do one together.
Whatever you want
You
to
can
say.
fold it up and then, no.
Melinda, whatever you're going to say, if it's smaller, don't say it loud.
Unfold it, it shouldn't exceed the size of this,
Yeah.
okay?
You said on the review sheet, I'm sorry, you said x had to be less than or equal to 10? And it's
Greater than?
greater than or equal Oh, and then it could be 5, but 10 is better.
Yeah,
Okay.
yeah, exactly. Greater than equal to 5 is good enough. Greater than 5. All right, wait, what was the last problem?
39.
Right? Okay, so you're given x is exponential 1, right? And y was log x. Is that right? Okay. All right, so first of all, let's write down what is your distribution function of x. It's 1 minus e to the negative lambda x, which is e to x. 0. We also know x takes values greater than equal to 0. Okay, so then as x takes values less than 1, but first of all, so that means log x makes sense because you can't take log of a negative value. So that's good that x only takes non-negative values. When x takes values less than 1, log of a number less than 1 is negative, right? And as x approaches 0, this log goes to negative infinity. As x increases to infinity, log of x goes to infinity, right? So y takes values in the whole grid model.
So this one is with the lambda x to the...
Yeah, it's e to 1 minus e to the negative lambda x, but lambda is 1 in this problem. You're given that lambda is 1, right?
Yes.
Yeah, okay, yeah, so you're given that lambda is 1.
Between like this and 32, it's different distributions. It's a modular.
32, was that 32?
That's 37.
What was 33? 32, your lambda is 1/2.
Yeah, but it's the same distribution.
Yeah, so in 32 you were given it's exponentially distributed, but lambda was 1/2. So exponential 1/2, so here you have negative 1/2 x.
Oh, this is the non-calculus one?
Yeah, this is the distribution function I'm writing down, not just the density function. So your lambda is whatever comes out here.
Oh, this is not the density function.
Yeah, this is not the density function. All right. If you want the density function looks like this. It's lambda e to the lambda e to the negative 6. That's your density function. But for the most part, I think we would need only the distribution function for this. All right, so we figured out the values of y. Yeah.
It's not the natural log, it's the log base 10.
Oh, okay. Well, let's just change the problem to natural log, because log base 10, then, you know, you have to write as 10 raised to that, and it is more natural to work with exponential distribution. So I think when they say log, log, they mean natural log,
Well,
they just don't write.
It gives y equals log x in the book.
Okay, yeah, so
Yeah, but
technically that means
sometimes-
log base 10, but let's take the question to be.
Some things though, that's actually, the convention is that's natural. What was I thinking of? Some like online equation
Yeah,
that I
some
was
people
using.
use, it's like, I know that I sometimes write log x when actually I mean natural log.
Right.
Okay? Because actually log base 10 is not base 10 is not a number that appears naturally. It's actually exponential is the one that appears naturally, log base e. So let's work with this, because this is the thing that if you find like constant in nature, it's always something base 2. All right, so we are doing the problem for natural log. You will do something similar for log base. All right, okay. So first of all, fy of y. So take y, any number plus infinity and between negative infinity and plus infinity. So for this, look at a distribution function. By definition, a distribution function is just the probability that y is equal to this little y. So that is probability that your random variable is natural log x less than or equal to y. And so now let's solve for x. X is less than or equal to, we raise both sides to the exponential raised to that. It's just going to be the y. So if log x is less than or equal to y, x is less than or equal to e to the y. All right. Okay. So this is the form probability x less than or equal to some number. That is just your distribution function at this point. Right. So now you have this equals, differentiate both sides. See? So differentiate both sides, you get the density function of y at the point y here. Here you get the density function of x at the point e to the y times the derivative of e to the y, which is e to the y. So now differentiate both sides. We get, so differentiating we get, that's what you get to both sides.
Yeah, I'm sorry, why is it e to the y?
Here, so log x is less than or equal to y.
Right.
So the x, so solve for x.
Oh, okay, I'm sorry.
So you just take both sides, raise it, and e to the y. Okay. So basically we're just undoing log to solve for x, so x is less than or equal to e to the y, and so this is just fx of e to the y. Everyone with me so far? So the density function is, let's write this down again, e to the y, so e to the y. So if you actually want to write this down, what is your density function? It's lambda is 1, so 1 e to the negative x. And note here, fx of e to the y can be negative, but e to the y is always positive. So we always. So remember, your density function for y is defined is non-zero for, in the whole, over the whole real line.
Now, can you bring that y down? Like, oh no, that's only, there's like a line, right? Because isn't,
Where?
in the second part of that, where it says e to the negative x to the y?
E to the negative e to the y.
Oh, okay.
So x is whatever the x is here,
Uh-huh.
and it's e to the y.
I see.
I'm just plugging in my f of x from here. So I'm reading off this. It's e to the negative x. If it wasn't 1, it was lambda. I'd have lambda x here. I'd have negative lambda times e to the y. If x is exponential lambda. Oh, and then I have lambda here too.
Dr. Kumar, I noticed reading over break that the bounds on y, sometimes the book does it with it, sometimes it does it without it. So how important are the bounds?
Well, it is really important. Like, I would like you to write down the values of, the values that y takes. Ideally, when you finally write it down, I'd like you to write down like this, like a formula with what value is this defined like this, and if it's defined as 0 outside of that. Now, here you see it was definitely important to first check what values y takes, because you realize that while x takes only non-negative values, your y is taking everything, the whole real line. So I am also looking for that. I'm looking to see that you realize that when you take log of x, now you can have your random variable can even take negative values. So I do want to see that you are going to calculate this distribution function for y anywhere in your real line. Yeah, so yeah, I'd like you to write that down. Sometimes in the book, sometimes in the book they only write down the density function where it's non-zero, right? Okay. So yeah, sometimes people don't bother to write it when it's 0. It's just sort of understood that that you're only going to define it where it's non-zero, and it's understood to be 0 otherwise. Yeah, but on this exam, make sure you write out where it's non-zero and where it's 0. Okay, any other questions? Even if you stopped here, you didn't go on to write this, you've written this, fx of e of y, and if you've written this somewhere, and you've written this, you will still get full credit for it. So all I've done is taken all those 3 things and put them together here. Taken that this is your formula, put in the formula for this, and I've also put in the range of values for y. But as long as it's somewhere in the work, like range of values of y, the formula for fx, and you find the formula, then you get full credit. Okay. Any other questions? So we've covered right? You speak. And any questions on the previous homework problem? So I remember on one of the early homework problems you had these conditional probability questions. Everyone's okay with that? This thing was a 6-foot question. Oh, okay then. Nothing more to say.
Do you have homework after the break?
Yes, okay. So please let me homework before you leave.
Anyone heading towards Southfield? And you'd be willing to give me a ride home? Great. If anybody wants links to these videos of lecture, get my email address and email me.
Wait, what?
Huh?